welcome back. In the last two lectures, we have introduced with tree, the various properties of tree. Then we have seen one special tree, that is binary search tree, the insertion and deletion in binary search tree. So now we would like to see how we can implement a tree, especially the binary search tree. During this session, we're going to see. So during this session, we're going to learn how to implement binary search tree using the programming language C. Mainly we'll see the linked list based representation. If you can recall, in the last lecture we have discussed about that in two ways we can implement binary tree or binary search tree, that is using array and as well as in linked list. Now you will focus mainly on linked list based representation, and then also we're going to see some basic idea how we can do it in. At the end of the lecture, we will see that how we can implement array based representations. So we'll see how to create a tree, especially through the iterative process of insertions to create a tree. Then one of the traversal we'll see, that is by in order traversal, and then also we'll see how to search in binary search tree. So let us move to our implementation. So in the last lecture we have already discussed that to represent a tree we need the node and edges representation. So to create a node we need some kind of structure. So the structure node, so you are going to create a node, that is a structure node, and it will going to contain basically three elements. One is the data or info part, and then the two are the left pointer for the left child node and the right child node. So this way we are going to create or define a node data structure. Now obviously when we do some big program, we try to reduce the size of that to write iteratively stack node stack to every time. So to make it smaller, we'll use type def and then convert it into ND. So now onwards we're going to refer stack node as ND. So we're going to create every time a new node, that is a pointer we needed of type structure node, to hold the address of the newly created node. And how to create? We're going to use the malloc function, and then we'll, after creation, so we'll go the address of that location will going to be held by the pointer, that is new node. So let us recall the if you forget, somewhere that what is actually the BST, because next slide onwards we are going to discuss only on the insertions in and in traversal in binary search tree. So binary search tree is nothing but it's basically a order tree where any node's left child should have less than value from that root value itself or that node value itself, and all right subtree contain all the higher value than itself. So the left subtree of 12, this is the 12 root node, is all less than 12, and the right subtree of 12 is all greater than 12. So even in case of this 5 subtree headed by 5, all its left side is less than 5 and all its right side is greater than 5. Now to start, what we have to do, we have to have a kind of a pointer that will going to hold the first node or starting node of that particular tree, what we called it as a root of the tree. So we will going to create a pointer, we are going to hold the address of the first node. So obviously when there is no node, we will have to initialize that particular pointer with null value. So we'll assign first null value, and then what we'll do, we're going to create or invoke a function that we're going to write. I'll discuss in the next slide, that we're going to create our own function, that is insert BST, and then we're going to pass two parameter. One is the address of the that particular pointer who is holding the address of the first node, and the value that I'd like to insert in that particular tree. So why I am sending the address? Because from the function itself I have to replace the value of the that root node, the value of the pointer, because if it is the first node I am going to put it from the function. Naturally I have to update the root point, the pointer which is holding which is supposed to hold the address of the first node. So let's see how my functions look like. So as I have said, I am creating a function that is insert BST, and the functionality of that method is something like that. It will going to return 1 if it is a successful insertion, and if it returns 0, then it will going to be an unsuccessful insertion, because of the unavailability memory, it may happen some unsuccessful insertion. Otherwise it is always going to be a successful insertion. So it will going to take two parameters, as I have said. It's basically taking a double pointer of type ND to hold the address of the pointer who is holding the address of the first node. So here what we are sending, the address of the root, and then root means not that first element. Root means the pointer which is holding the address of the first node. In terms of tree, the first node is basically our root of that particular tree. So don't confuse with these two root. One root that I am using over here is basically the pointer variable who is holding the address of the starting node, which is actually the address of the root node, and k is obviously the value that I'd like to put it over there. Now if you can recall, we have already discussed in our previous lectures then how to insert. As and when you are try to insert any node, you have to check with every node with their value and the node that you'd like to insert. If the node that you'd like to insert, if its value is greater than the current node value, so obviously it will go to the right side, and if it is less than that, then it will go to the left hand side of that particular node. And that the same thing we are going to follow as and when we are moving down through the tree, and then it will follow and then when we are going to insert till we reach the end of the tree. That means until and unless we are reaching to some null node or null, we'll go on continue that particular traversal. Now for the first node, it is obvious that the pointer that is called root, which will the content of that node will go, the content of that particular pointer will going to be null. So looking into that, we can easily check whether my tree is empty or whether my tree is already existing. So there are two ways that we have to do it. Either it's a first node that I am inserting in my tree, creating my tree for the first time, or I am going to insert any node which is in a tree which is already existing. That means in that case my root is not null. So to do that thing, I am using three pointers I am using of type ND. New node is to hold the address of the newly created node, and the car pointer and parent pointer are just to traverse through the root, traverse to the tree to reach to the final node and to get the target node in which I am going to attach my new node. So that is why I am using two different pointers. So I'll come to that. I'll show how. I'll show you how to. What is the use of that car pointer and parent pointer. Now, obviously, these are the routine statement that I have to use it. That is, you have to create my node as I have discussed. So new node, you have to create a node. You have to use malloc, and then you return it will return the address of the newly created node and will going to be held by the pointer new node. And then we will check it whether my memory allocation is successful. If it is not, then it will going to return null. So by checking it, we will going to return 0. It means my memory allocation is not successful. So So in the main part of the program or in the main functions, we will check it that value, the return value, and then we'll say whether my insertion is successful or whether it's my my insertion is unsuccessful. So if it checks, if it is 0, naturally it's an unsuccessful. We are going to give a message that my insertion is unsuccessful. Now once my insertion is successful, and most of the cases it will going to happen, in this case what will happen, we will going to initialize the data part of that new node with k, that means in this part of that node I am going to assign that new value that I would like to insert over there. I'll put it over here, and then the left child pointer and right child pointer I'm going to initialize with null value. So here while initializing, I'll initialize the data part with the value that I'd like to insert, and then left child and right child initially going to be initialized with null. So this is what I am going to do it in what is called for creating a node and initializing that node. Now I have to link with the tree. So first thing is that obviously at the very beginning, when there is no existing tree available or during the implementation, so if it is the first node, obviously the root node I am try to insert, then how I will check it whether it's a first node or not? Just simply check the content of the pointer r, not content of the r, content of the location where r is pointing. So that is the actual our intruses our root that we have created at the beginning. So that root content of the root net we are going to check it from here. If it is null, then we'll assign the address of or the content of new node which is there inside new node to the r. Star r means the location content of the root. So this way we are going to make a link between them, and obviously we are overwriting null, and it will now going to contain the address of the first node, and then you can give a message that yeah, we have inserted a first node. However, this is optional, you can omit that printf options. Now let's see if since it is a first node we have already created, that means that tree is now existing, and that means root is not null. In such case, how are we going to insert another node? Let us assume I have already created a node with the element 5, and then obviously since there is no subtree available for other than this is the only node which is there in that particular tree. So naturally both the left child and right child will going to be remain null. Now I want to insert another node, that is 23. So obviously what we have seen will in the last slide, here also we are going to create exactly the same way, and from the main we are going to pass that value, and then we initialize or assign the value to the data part of the new node, and right child and left child will going to be null. So here in this case, in this example, the k is basically 23. Now I have to put in its correct position according to the BST rule. So we'll go on traversing the tree until and unless we reach the end of the tree. So that's why at the very beginning what will happen, we cannot change root. So we'll take another temporary pointer variable that will help to reach to the end of that particular traversal. So we'll take a variable called car, and then we'll assign the content of root. The content of root to that car, so that since it is containing the address of the first node, so now onwards after that, let us assume car is actually start pointing to the first node, that is the actual root node of that particular tree. Now since we reach we go on traversing this till we reach null, so but we need that target node under which we are going to attach the new node. So that's why what we'll do when we'll go insert in a iterative process of traversal, what we'll do, we'll always store my last visited node into another pointer that is called parent. So what will happen, we'll assign at the very beginning the content of car. So content of car is basically nothing but in this example is the first node. So what will happen now, after assigning the parent pointer also it will start pointing to the first node. Now we'll check it if the car arrow data is greater than k or not. So here in this case car arrow data is not greater than k. So what will do, it will go to the else part. So else part it will do, that means k is greater than actually the data, current data pointed by car, the pointer car. So we're going to assign it to the car. So left child, whatever content is there in the left child of the current car, it will going to be stored in car. So what will happen now? We'll assign null to that car, because that means we will write null to the car because we are taking the content of car arrow right child. So car is now become null. So it means my traversal is over. There is no node at the right hand side of the tree. So but parent, you see, parent is still pointing to my root node, which is actually my target node for attaching my new node, that is node labeled with 23. Now in the next iterations, what will happen? Car not equal to null condition will going to be false. Then what will happen? It will not go inside a particular loop. Then it will come to the remaining part of the program, that is it will check again, but now it is checking with the parent because car is null, so we cannot check with the car. So parent arrow data, whether it is greater than k, so parent arrow data whether it is greater k is this, so it is not greater than that, so it will going to come to else part. So what will happen? So parent arrow right child will going to be the new node. That means this is the parent arrow right child means this. So we are going to assign, this is new node. So address of the new node will going to assign to this particular right child. So what will happen? Consequences that it will start pointing to the new node, and this is going to be my right child of 5. So let's see with one more example. Let us see one more node that I would like to insert, that is 3, which is basically the less than 5. So again, since it's we have to initialize my new node, you have to create that node, you have to initialize the node, and then you have to make right child and left child as null, and then now we have to put in its correct position. So again, naturally, since its root is my root is not null, it is already existing tree, so it will come to the else part. Then again, I am going to take the help of a pointer that is called car. So now car, again I will take the content of root. So now car will start pointing to the root node. Now we'll transfer like the previous case. We'll take another help of another pointer that is called parent. So parent will transfer that value of car. So parent is also pointing now to the new node, the root node, actually the new node. Again I am checking car arrow data, whether it's greater than whether it's greater than k. Yes, the car arrow data is greater than the current k, that is 3. So naturally what will happen? It will going to do car equals to car arrow left. So it will check, that means as per rule, if it is less, naturally my traversal will go towards the left hand side. Now since left hand side there is no tree available, so I can insert that new node into that particular left position. So now the car become null. Then it will, in the next iteration, it will come out because car become null. Now it will check with the parent. So parent data, again it is checking, since parent arrow data is greater than k. So parent arrow data is greater than k. K is this 3. So what will do? The parent arrow left child, it will going to be, this is the parent arrow left child. Parent arrow left child will going to assign in that the address of the new node. So what will happen? It start pointing into that. So this way the same process will going to continue for any newly arrival node. So if it is a less from 5, it will go to the left hand side. Again it will check with 3. If it is greater than 3, it will go to the right side of 3. If it is less than 3, then it will go to the left hand side of 3. So this way, if you go on continue, you can insert as many number of elements into to create a binary search tree. Now let's see how to do we have seen in the last two lectures that we can traverse a tree, we can move through a tree using three different traversal method: pre-order, post-order and in-order traversal. But here we will see in-order traversal. Programmatically, there is a very minor difference in just the positions of some of the calls, in the statements, the alteration of the statement in terms of in-order, pre-order and post-order traversal function. If you are using recursive call, see here in my program I am using recursive call for to traverse in the left hand side or to traverse in the right hand side. So let's recall what exactly the in-order traversal says. It says I mean, if you can remember, I have already discussed in the last lectures, like in case of in-order traversal, we will not going to process or print that node value until and unless we base it for the second time. In pre-order, the printing is happening in the first traversal or first visit, and in case of in-order, the printing is happening or display is happening or process is happening in the second visit, and in case of post-order, it is happening will display and then in the third visit. So how it is happening as per the in-order traversal, what it says, that first we will go to the left hand side, we will finish the left hand side traversal, then when coming back we will going to process that node, and then we will start traversing the right hand side of that tree of that node, and then we will follow exactly the same thing for every node. That for every node, first we will traverse the left subtree, then the node itself, and then go to the right subtree of that particular node. So that's why exactly the following the same structure the function has been created. So first we will go to the left child, then while this left child traversal is over, then it will print that particular data of that particular node, and then it will go for the traversal for traversal for the right subtree. So how it is happening? Since I am using here, and most of the simplistic implementation is what is called the recursive call, using recursive call, though you can do it using non-recursive call also. But the simple, why it is simple? Because the number of lines are very less. It's more disciplined code, I should say, because now it's nicely, because of the recursive properties, it can nicely do the same thing for the entire tree. Now since it's a recursive call, let me show you some type like how it is happening during the call using stack. Stack function call. Basically at the very beginning we are going to pass the root node. Here we are actually sending the address of the node, but to understand this picture, the example, for simplicity, I am, instead of using address, I am using the node that I am visiting. So first node that I am sending is 5. 5. So naturally it will going to remain in the stack, that is 5. Then after that, once it is go inside with the 5 value, naturally this is not null, so it will not going to execute return. Then after that, as per my program, it will going to call again it will going to call recursively the function in order by passing the address of the left child. So the fifth address of the left child means basically now here is 2. So I am now passing 2. So as and when I am replacing these things with the node 2, so again there will be a fresh function call for in order. So now it will going to still, it will remain. I am not going to touch now the 5. Now I will concentrate with the node 2. So now this is like a fresh call. So I will consider it as a fresh call. So now here the node that I am passing is 2. Now the 2 is not a null, so it will not going to return. So again it will execute ptr arrow left child. So ptr arrow left child means the left child of 2. So ptr left child of 2 that I am now invoking. Now what is the left child of 2? This is basically null. So that means this is null. So that means after calling ptr arrow left child, that is the null, it will go inside a fresh call. Then it will check, yes, this is a null. So null means it will return. Where it will return? Return to this part of this call. That means this will return. Now if it is returned, then that means this is also returned. That means this execution is over. The ptr arrow left child is execution is over. Now still I am in this function. This means now still I am this function. So that means I am going to the next line. What is the next line? Printf that value. So that is 2. So I am putting print output 2 here. So now what will happen? Since this printing line is over for the node 2, then I'll go to the last line, that is in order ptr arrow right child. So now I'm calling ptr arrow right child means 2 right child of 2. So what is the right child of 2? That is 3. Okay. So now 3. Now again it's a fresh call. Now I'll check it whether that 3 node, this is not a null node, so it will not going to return. Then for that 3 also I have to it will call, or I have to traverse the left child of 3. So I will going to call left child of 3. So this is already in the stack. Now again this is this is null. So this is null. So it will check here. It will going to be a null node. So it will return. Return means where it will return? It will return to now this line. That is, it will execute now the printf. So what will do that thing? Now it will print 3. Now after printing 3. It will go for the right child of 3. So it will now execute right child of 3. So right child of 3 means basically it's a 4. So now again fresh call. So 4 is not null. So it will not execute return. So it will come to the in order traversal. It will go do again the in order traversal by passing the left child of 4. So left child of 4, it will do that thing. Then when it will do, it will basically left child is basically null. So it's a fresh call. Then it will check it. Once it is passing the left child of 4, it will going to be null. So it will check null. So it will return. So return means now these lines are over. So what will happen? It will print the value 4. Now after printing 4, now one more line is left for 4. That is going to the right child. So it will go to the right child of 4. Now once it goes to the right child of 4, this is again, it's basically it will replace with null. So it will go now right child is null. So it will check it over here. So it will return null. So now that means my last executions of that for call with node value 4 is now over. So this is over since it's returning. So that means 4 arrow left line execution is also over. Now it will return to the that means this line is over and it is done from 4 value. So 4 is that call is also will be popped up. And then since it's called by after going to 3 arrow right child, so this is also going to over. Now that call for 3 is also over. And then since it's called from 2 arrow right, so that is also we're going to remove. Then that means from here we are moving to 4, then go back to the not node, then it call back to go back to the 3, then it will go back to 2. So now what will happen? This is that we have come to that node 2 because of that call from ptr arrow left child. So that also now over. Okay, still 2 things is remaining. That means 5s. When I'll come back to the 5s function call, the left child is now returned. Now still I have printf 5 arrow data. That is I have to display now 5, and then I have to go now for the right child traversal. So naturally it will going to print now 5. So this line is over for 5. Now it will go for the right child traversal of 5. So what will happen? This way it will traverse the entire right subtree of 5. Then once it become visited by all the nodes in the right subtree, so I'm going to call this. So now once it all become visited, I have displayed all the nodes. Then what will happen after because it's recursive, from 15 it will go back, from 23 it will go back to 15, from 15 to it will go back to 9, from 9 it will go back to 5. Now once the 5 is over, so that means my first call, that is from the root value, it will going to be popped up from the stack, and then I'll say my traversal is complete. So this way you can do traversal, in-order traversal of any arbitrary binary search tree. And the thing here is that in case of post-order and pre-order traversal, only difference is the order how I am executing. So in case of pre-order, I will going to print the data first, then I'll go to the right child traversal, then I'll go to the I'll go to the first left child traversal or left subtree traversal, and then I'll go to the right child or right tree traversal. Similarly, in case of post order traversal, I'll first go to left subtree traversal, that is left child traversal, then I'll go to the right child traversal, then after that the last line of that code will going to be the PTR error data, that is the printing will going to be at the end. So the entire thing will going to remain same, only the order how I am going to call the left child traversal and right child traversal. And for I mean, to make it different, you can have different name for the function. One, it is in order, so it may be pre-order, it may be post-order. Now next, see how we are going to search a binary search tree. Searching is somewhat similar with what we have seen in case of insertion, because while we want to do any insertions, you have to do a searching. Then you have to go to the positions where you would like to, what is the exact position of that particular node that you would like to insert, and then only you can attach or insert that thing. So that means you have to do first the searching and then only you can attach. So let's see, I mean, simply what is actually the search, how it is happening. So we're going to write a function that is called search, where we're going to pass the content of the root node, that is root pointer. Here we will not going to use double pointer or the address that I am not going to pass of the root pointer, because here I am not changing anything, I am just traversing. So that's why I am sending the address of the content of the root, that is the address of the root node of the tree. And then I'm sending or passing the number or the element that I'd like to search in that particular tree. So while so it's basically a continuous process. So what will happen? So this is also an iterative process, exactly the same way what we have seen similar to that, the during insertions. We're going to take at the very beginning the root of the PTR, the pointer PTR. It's a temporary variable which is there inside that search function. So it will going to start pointing to the first node. So let us see with an example how I am going to search a particular node that is called whether it is present or not, that is with the value x3. So x value is going to be transferred to the value k. So now I'll check it inside the function, that value 3 is present or not. So if my search is successful, naturally I'll going to stack to a node with that equal value of that particular node. That is the data part of that. And if it is not a successful search, that means if that number is not present, then it will come till a null value. So that means if we reach to a null, so that means my search is unsuccessful. And if I get a node where the root data value is equal to the value that I would like to search, then I'll say that number is, or the element is present. So the very beginning, if my tree is not empty, so naturally my PTR will not going to be null. So PTR will start pointing over there, and then I'll check it. The data of that currently pointed by the pointer PTR. So in that case it is 5. So what is that? The k value is obviously less than that is k in this case is 3. So the k is less than 5. 5. So naturally what will do, the PTR will now go to the left child of 5. So what will happen? PTR become PTR equals to PTR arrow left child. So PTR arrow left child is this address, that is the address of this node. Now PTR will start pointing to I'm not showing through animation over here, but what will happen? PTR now start pointing to this particular node. Okay, and then again it will, since it's not a null, then again it will go inside. Now what will happen? Now PTR is pointing this node, particular node. Then it will check whether PTR arrow data is greater than k. No, my k is 3 and PTR arrow data is also 3. So it is not greater than, it is not less than. So obviously it will come to the else part, that is it will return 1. 1 means my search is successful. Okay. So once it is returned 1, then we will check it in the main function, the return value 1 or 0. If it return 1, then we will say the success the element is present. If it gets a 0 value, then it will say the search is unsuccessful. Now see one more example where my search is unsuccessful. So 24. Again it will going to start with that. It will take the root address of the root node, and the starting node, and the value over here, the k is actually 24. Now at the very beginning, PTR is basically pointing to the first node or root node, so it is not null, so it will check it with that. So PTR arrow data here is greater than, that means PTR arrow data is less than the value that I would like to search. So naturally what will do, it will go to the right child. So the PTR value will start pointing to right child. So from here it will take the new nodes, the right child address. Then now PTR will going to point to this node, that is 23. Now once it comes to 23, then since PTR is not null, again it will go inside. Now my PTR arrow data is 23 and the value that I would like to search is basically 24. Now obviously the else if condition will going to be satisfied, that is 24 is greater than 23. So it will execute PTR equals to PTR arrow left right child. So PTR arrow right child is how much? Null. So I am assigning actually null to PTR. So during while I will iterate, PTR will going to become null. So it will not going to execute the while loop. So it will come back, come out and execute the last line, that is return 0. So return 0 means the search is unsuccessful. That means 24 is not present in that tree. So this way you can take any arbitrary size binary search tree, and you can say whether my search is successful or unsuccessful. Now with that, you have to try yourself. Because we have discussed about linked list based representation of a binary search tree. Then also you have seen you have to do array based now binary search tree traversal. We have seen pre-order traversal, we have seen post-order traversal. So we have seen in-order traversal. So you have to do of your own the pre-order traversal implementation and post-order traversal. Now how to represent a tree, binary search tree in an array, that is through process of iterative insertions. Let me discuss with a simple example. Let us say like my previous example, these are the values that I have to like to create a binary search tree. So if you can remember that the first node always should be the root node. So root node always going to start from array index 1. Because why array index 1? Because we have seen to go to right child of a particular node in an array based representations, we have to do some simple mathematics like 2i's I or 2i's I plus 1. That means if we want to go to the left child of a particular node, then it will going to be 2i's I. And if you want 2i's I plus 1. If you want to go to the left hand child of a particular node, then it will going to be 2i's I index. So say for a 12, what should be the left hand child will going to be stored? Where it will going to store 2i's I plus 1. 2i's I plus 1 means so right hand child of 12 is 2i's I plus 1, that is 2 plus 1, that is going to be in the 3. Left hand child of 2 will going to be in 2i's I. Okay, so that is in 2. So let's see how we're going to store 16. 16 is greater than, first we'll check it with 2. This is the first node. So now we'll go to the right, since it's a greater, so we'll go to, it should be in the right subtree or the right node of 12. So right node of 12 is basically as per that formula I'll show you here. that is right child is 2 to the power I plus 1, that is 2 1 plus 2 plus 1, that is 3. So 3 is the position. Since 3 position is blank, its no value is there, that means my right subtree of 12 is empty, so I can store it over here. And then let's see 19. 19 first I'll check it from the root, so that is 12. So from 12, since it is greater than 12, so it should go to the right side. So right side means twice I plus 1, that is in 3. Then again 3 is already filled, so and 19 is greater than 16, so it should again go to the right side of 3. So right side of 3 means 2 into 3 plus 1, that is 7. So I'll go to the 7 index, then I'll check whether it's empty or not. Since 7 is empty, then I'm going to store 19 in 7. So again next is 5. So what is again I'll check it with 1. So 5 is less than 1. So 5 is less than 1 means it should go to the right child. Right child means what is the position? Twice I. Twice I means it's 2. So I'll going to store 5 in 2. Similar to that, I'll going to store 3 in the left child of 5. That means first I'll check with 12. 3 is less than 12, so it will go to the left child. So 3 is less than 5, again it will go to the left hand child of 5. So what is the left child? Left child means twice I. Twice I means 4. So I'm going to store 3 in 4. Similar to that, I can store the value 7. So this way you can think of your own, and you can implement very simple implementation for array based binary search tree. And in the same way, using same recursive call, you can try for pre-order, post-order and in-order traversal in array based binary search tree. So this is the structure. If I take a binary search tree to show you, this is the structure that the tree will going to look like, even in case of array. Normally, I mean, if you can remember, we have discussed that thing, that every number we are actually marked with starting from 1. So this is 1, this is 2, this is 3, this is 4, this is 5, and since it's empty, but we'll continue that counting. So this is 6, this is 7. So there are basically seven array of size 7 we need it to store this particular tree. So what is the size of that array should be maximum size? We have already discussed in our last lectures. So with that, I would like to conclude or end my this current lecture. Thank you so much.